Okay, welcome to the lesson on centripetal acceleration and force. So what's our goal today? I want you to be able to explain and determine the value and direction of centripetal acceleration and force for real-world situations. So in order to do that, we're going to have to go back and talk about exactly what's happening when we're talking about this centripetal acceleration. So if we have an object traveling with uniform circular motion, so think of yourself on one of those rides that spin around, or in the old days, back in my day, the playgrounds had the toy where you jumped on, you pushed it like crazy and jumped on, and then people who weren't hanging on tight flew off the side, or people threw up. It was the coolest playground toy ever, and obviously it had to be removed because it was too much fun. People were getting hurt as they flew off, but still really cool. So if you're going in circular motion, so it's like any of the fair rides where you're going around in circles constantly, you're undergoing a centripetal acceleration. So that means that the velocity of an object traveling with uniform motion is tangential to the path. So what does that mean? That means if you were going around in circles, that anytime you let go, you would travel in the direction tangential to the circle that you're traveling. All right, so those arrows, I just threw random ones on there. So if we find the center of the circle, which I'm going to say is there, going by my most accurate eye, that these lines draw into the middle, they're all perpendicular at that tangential. All right, very important when we talk about the math. So if this is your velocity at 1, here's your velocity at point 2, here's your velocity at point 3. So these points are the points that we're interested in. You would agree with me, hopefully, that the magnitude of your velocity is equal at each location. However, your direction is not, and that's why I'm using magnitude symbols here. So the magnitude of the velocity is the same. So if you were to let go, if you were being spun in a circle and you let go at any point, you will travel tangential to the point where you released to that circle. So let's look at some of the vectors, vector addition it is to get to where we want to be. So if we calculate the acceleration of this motion, we can use the formula delta V, so the change in velocity, which I need to put some vector symbols on, is equal to V2 minus V1. So let's pick 2 points on my circle, and you can sketch in the arrows however you want. So I'll try to keep this as accurate as I can. So here we are, our 2 velocities. So at point 1, we have V1. At point 2, we have V2. And again, they connect to the center of the circle, right angle, because it is tangential. So we do our calculations. So we start with delta V equals V2 minus V1. So I'm going to, through the magic of, I was going to say Disney, but it's not really Disney, not quite that caliber. I'm going to take my V2 vector, I'm going to put it over here. My V1 vector, I'm going to clone it as well. And because we are subtracting it, I need to change the direction of the arrow. So what I'm going to do is, I'm going to simply cover that arrow with a dot. And you'd be asking what kind of vector addition is he doing, to be quite honest. So let's try that again. I have to go to the V2, the head. So I'm putting the arrowheads together, but it's not, because I'm going to do subtracting, so the arrow actually changes direction. So V2 minus V1, which means that my resultant vector will start here and end over here. So there is my resultant vector. Here's my V2. Here is my negative V1. All right, so next step. So what does this mean then? Well, the information we can get from that triangle I just drew, let's talk about it for a second. We know that your velocity, magnitude of velocity hasn't changed. So therefore, we know that the magnitude of negative V1 is equal to the magnitude of V2. So those two magnitudes have to be equal. Now these two vectors are acting perpendicular to each other. And what happens then, or what's created, is that because these two magnitudes, these two vectors are of equal length, I'll just put that in hash marks. If they're of equal length, then what happens is that these two angles down here are the same. So for argument's sake, and it works if it's not, but it's easier to see. So assume V1 is perpendicular to V2, then the angle would be 45. All right. Does it have to be perpendicular? The way I have it drawn, it doesn't really look perpendicular, does it? So the thing to remember here then is that because those lengths are equal, what happens is that, if I draw the radius in a similar direction, okay, so if I draw that the same length, and here would be my, what I'm trying to show is that the resultant is going to point here because it's at a 45, it's going across the diagonal of the box that's created. And the box that's created is that V1 vector. So V2 minus the V1 would be pointing in this direction. All right. So V1 is perpendicular to that circle. So that means line drawn out is perpendicular to it. So we end up with that resultant pointing toward the middle of the circle. So I know in this case I took I assumed it was 90 degrees, so it's a little easier for you to kind of visualize, but it doesn't have to be. It's just the way I've drawn it, I freehanded it, so I don't have exact angles to kind of match it up. So unfortunately, you're going to have to kind of take my word for that. If you want to see it, we can measure this out and go through it in class, so you have some visual proof if you're having a tough time visualizing it. But the general conclusion I want to generate here is that the acceleration for an object traveling in uniform circular motion, for an object traveling with uniform circular motion is always pointing in the direction of the center of the circle. What I really should have done is I should have drew my V1 and V2 vectors up above shorter than the radius of the circle, just to help kind of keep things in perspective here. But like I said, we can go through and I can show you the geometry in class. It's a little bit easier if you envision that V1 and V2, I took them from the two perpendicular to each other, which I kind of drew that way because they're equal magnitudes, the sides of the triangle. So this side and this side, or in this case this side, are equal lengths. That would mean that it's a 45 here, which means that it would end up pointing toward the center of the circle. So like I said, you want to see that run through and show you the exact nature of how that works, definitely challenge me that in class and we can go through it to help kind of visualize it. But this is really the whole point here. All right, is that if you're going around in a circle, you're always accelerating to the center of that circle. So let's talk about some formulas here, so we can do the actual calculations and apply it in the physics here. So I've got two circles drawn out for you here. The first one we're going to call it a radius vector. All right, we got your two radius vectors here. So what that does is that creates a pi wedge. Let me draw that properly. That's my theta. That's my radius. And what we know is we're talking about the displacement of an object moving from point 1 to point 2. So that would be our delta D going around the outside. Now, we can find our average velocity. So remember that if we're looking for your average here, you're looking at, or your displacement, sorry. Displacement is equal to your velocity multiplied by the change in your time. Now your displacement here from point 1 to point 2, I kind of drew it on the edge, but remember displacement is how far you are from your original location. So delta D should actually be a direct line from 1 to 2. That is your delta D. All right. In the triangle below here, or in the circle below, so I'm going to say this is diagram 1, continuation. Diagram 2, let's take a look at it for a second here. So I'm going to do a little bit of geometry here. So if I label them before I get going, I'm going to call this V1, I'm going to call this V2. And if I move V1 and V2's tail to the same location, so I'm just going to clone it, I'm going to move it in, so it's drawn just like that. So that is now also a V2. And I find the angle between the two vectors, V1 and V2. Well, we know that the angle is 90 degrees. I'm just going to change pens here. I know this is 90 degrees. It's a property of a tangent to a circle. All right. So if that's our 90, that means that if I construct that triangle, or I move that bottom part, that angle would then be 90 degrees right there. So for people that are trying to see where I'm drawing, that angle has to be 90 degrees because this one was 90. So I just shifted it, which would mean that this angle right here is 90 minus theta. So what's left in a 180-degree triangle? We know that the angle between that radius and the V1 vector has to be 90 degrees, which therefore leads us that the angle between V1 and V2 is simply theta. So our resulting diagram, and I'll try to do it in the same direction. So V1 is heading that direction. V2 is heading in that direction. The angle between them will be theta. And the difference between is the change in velocity. All right, so here's a qualifier then, and this is where the sort of the extended physics comes in, and that's the assumption that I've got written down below here. So we're going to put an assumption in. So if theta is really small, all right, so it's drawn such that those vectors are a fair distance apart, but if it's really small, we can assume that V delta t is a line. Okay, so going back up to the original diagram, this distance here, if we were to shrink that pi down really, really small, all right, such that the radiuses are almost touching, that is what's becoming a line. The curve gets so short that it becomes what looks like a line. So if we take our theta really, really small, then that V delta t becomes a line. We also know that the magnitude of V1 is equal to the magnitude of V2. So therefore, the two triangles shown so 1 and 2 are similar. Okay, so those two triangles that are up above here, they are similar for theta really small. So we're looking at theta being a very, very tiny number. If that's the case, then these two triangles are actually similar triangles with that distance being V delta t. And that's where I'll leave it in here, and I'll finish up this proof on the next to show you where these formulas then come from.